Okay, so we are very happy to have Timoteo Carletti with us from University of Namur in Belgium. And well, I have to say, I know Timoteo since a long time, since he was a graduate student. So actually, if you can tell the student just a few words about how you end up working in your area, what kind of path, that would be very...
Okay, of course.
Thank you.
So first of all, thank you very much, Stefanella, for the invitation. I think it's a very great occasion to speak with a lot of people, you know, all the world. Is one positive thing of this pandemic is that we have this kind of worldwide lecture so very easily. So yeah, so I just I have in the second slide my CV if you want. So yeah, I just recall that I will speak about complex network and dynamical systems, which is the core of my research. And indeed, the last lecture I will go a bit beyond the network. So I is a more general view than just complex network, because of the research is going quite fast, and so there are new directions that are already beyond the network. So okay, who I am. So I did my PhD in 2000 in Paris, both Paris and Florence, so Italy and France. And then I moved back to Italy, and then forth to France, and then back to Italy, where I spent 2 years in a Scuola Normale, so École Normale in Pisa. Then I moved to Venice. And so in the first period, say from PhD up to postdoc, I studied dynamical systems, but what is called holomorphic dynamical systems. So you have a complex function, analytical one, that you iterate, you look for a fixed point, is something like this. If you know the Mandelbrot set or the Julia set, they are all fractals that are obtained using this iteration of analytical function. Then I moved to Venice, and there I start to apply my background from dynamical system to biology, because I was involved in a project is called PACE, where PACE is a programmable artificial cell. So the project was to study the possibility to construct artificial cells that capable to do what you want. So it was a modeling part for me. And then I moved in 2005 in Belgium, here in Namur. And since then I'm working on I've been the head of the Equipe Stand Dynamical System teams. I've been the director of NAXIS. NAXIS is our Institute for Complex Systems. And so is a average size, I think, is 50 or maybe 60 person there. I think half permanent and half postdoc or researchers. And since I'm in Namur, I open even more my application field, including complex networks, stochastic processes. So the core, if you want, is dynamical systems, but then I'm moving toward the direction complex system. This means that if at the beginning of my PhD, I studied system in 1 or 2 dimensions, now I'm studying system with 100,000 or billion of dimensions. So this is the idea of complex systems. So let me introduce the motivation of this lecture, this series of lecture, and also of my research. So we can say that we live in an interconnected world. So you can think of almost any systems that you look around you, you can recognize that is made by simpler units that interact in some way, exchanging something. So here I copied 2 books, the one by Barabashi, which is one of the father of network science, which is now a 20, 30 years old discipline, but which has now a hardcore of theorems and results. And then I copied the other book, the one by Newman, and also Barabashi and Watts, that and I just copied a part of the abstract of the book. And you can see that in both cases, they start with networks are everywhere. There are any kind of networks. It can be the internet, it can be social networks, genetic networks, or friendship network, and so on. And they pervade our society. And so if we want to understand how the society behaves, we have to understand the network and also the dynamics running on top of such networks. So I'll give you a definition of network later, maybe next time. So just to define, if you want, a network, then a network is an object, a mathematical object, where you have basic units that interact. That's a network. So the units can be human, as in my picture, where you have this, each person is, say, oh, sorry, I have to use this one. So you have each person is a node of your network, and they interact because I draw this kind of link. So you can think that they are friends that interacts each other by exchanging information, opinion, likes on Facebook, also viruses, and so on. So this is a network where you have a mesoscale, where the basic unit in some sense is a person, a human being. But then you can go in a larger scale, where now you can think that a basic unit is no longer one person, but is a country. And so now you are interested in exchanging, for instance, how the countries, do they exchange goods, or they do exchange wars, or do they exchange person because of migration. So you understand that the notion of basic units actually depend on your question. It can be a human, or it can be billion or million of humans, because it depends. Or you can go, sorry, to a very small scale, where now you're interested, for instance, in brain dynamics, and now the unit are the neurons or group of neurons. So now you have very small units, that, but very many, because in the brain you have billions of neurons. So nodes are in the jargon of networks, and each one is connected to the other by synapses, where they exchange signals. And then now the network support actually currents, but this is a memory for us, action, thoughts, and so on. So you understand that the network is very basic or general framework, where you can put many kind of different systems, and really what defines the network is your research question. It can be repeated, single person, million of person, the brain inside one person. All these are different kind of networks. So so the question is now how to understand the behavior. For instance, how can you understand the global exchange market, or how can you understand the dynamics of the brain? So you have two approach more or less. So it's a rough division, but you have the first approach, which is the reductionist one. So you can think that you divide your system in small parts. You understand how each small part does work, and then you try to go back to understand the whole. So this worked very well in case of physics. For instance, all the particle physics, the grand unified theory that explain everything we know in the universe, starting from few elementary particles, is based on this idea that you can, understanding the role, the functioning of each particle, scale up and understand galaxies and so on. Or you have another approach, where you have this holistic approach, which is try to understand the system as a whole. And this is the core of complex system. The idea really of complex system is that you cannot divide the system into parts, because once you divide the system into parts, in some sense you lose the system. So the idea is that if you want to understand how memory works in the brain, you cannot split the brain into parts up to the neuron, understand how does a neuron work, because a neuron, it doesn't have any memory. It's just a cells that send signals and receive signals. So the idea of complex system is that you cannot split the system, because you lose the system. So you have to understand the system as a whole. And that in some sense is in opposition to the reductionist approach, which is very good in some cases. In other cases, you cannot ask the same question. So again, the approach that you use depend on the research question that you have. Okay, so let me now pass to the outlook of these 4 lectures. So because I don't know your background, I suppose speaking with Stefanella that you have very different backgrounds. So I divided into more or less 4 items. The first item, so I think will be today, maybe part on Thursday. So which is some basic fact about dynamical systems, because I don't know what you know about dynamical systems. So I will present you some basic ideas. Now you have to take into account that dynamical system is a huge research field with many subfields, so I cannot do everything in 1 hour. So I did a choice of some topics according to my feeling, according to what I will need once I will introduce you the network theory. The second point, I will introduce network theory. Again, I wrote a short introduction because I will not spend a lot of time by explaining all the details about network theory. I will limit myself to introduce the basic notion that I will then need in the application part. But I will, I already quoted 2 books, but I will cite again books and papers where you can find more information about the network theory, or if you are interested, just ask a question and I'll try to answer today or the next day. And then I will be able now, once I've done the first 2 parts, to study the network dynamical system. So in the first part, we will understand how a single dynamical system works. In the third part, we will put together such kind of dynamical system and we'll try to understand how the whole system behaves as a whole. So again, we try to model a neuron, so then we put a lot of neurons together. So we try to understand how the bunch of neurons will work differently from a single neuron. And then the last part, as I told you, will be beyond network theory, because even if network theory is a quite well-established theory, we are already on the edge. So we are now opening to new direction that I will show, where you can have several layers of networks. You can have a network that evolve in time, so temporal network. You can have stuff that are called hypergraphs, so higher dimensional networks, or you can have also networks where you have, in some sense, a continuous number of nodes, which is called graphones. So these will be all stuffs that I will show you in the last lecture. So let me start with the dynamical system part. So as I told you, this is a huge research domain, and so also the number of books available is huge. So here I choose 3 books. First of all, because I think that I think there are some echo. Okay, I think they are very good books where the authors really well explain the ideas. Maybe the Jordan is maybe a bit older than the other, or this the rules also is a very good one. The one by Steven Strogatz, I think, is more recent. At least there are several new publications, so maybe is the most updated for some kind of result that you're interested in. So the one by Jordan is maybe more theoretical one, where you can find proof and so on. The one by Strogatz and Verruls is more a presentation of result without too many proofs, by a lot of exercise and references to other books. So I invite you, if you want just to start, by looking at these 3 books, but of course there are really a lot of books. Okay, so let us start. So what is a dynamical system? First of all, you have to fix a first variable, which is time, which is, let us suppose, a continuous variable, which is so in R. And then you have a vector x, which has n components, so a small n. And this vector lives in some ensemble A, which is a subset of Rn, where A is called phase space or state space. What does it mean? It means that if I give you all the values of x1 up to xn, you will have exactly what the system is doing. So where is the system? So you can think that if this is a mechanical system, you need the position and the velocity. Once you have the position, the velocity, then you know everything about the system. Once you have the law of motion. So what is the law of motion? That you need then a function f, which takes value from A to Rn, our space, and this defines the time evolution of the system. So the rate of a variation of x of the state space, not that I will denote by x dot or the x over the t, is the notation by mathematicians or physicists is the same. So the rate of variation is equal to this function f. So let us know that because x is a vector, also f is a vector. So if you want to read it in component, then you have for all n component of x, you have n derivative for all the components, and each one is equal to one component of f. So x dot 1 depends on all other variables. And because you have a first order differential equation, because you have the first derivative with respect to time, you also need to add the initial conditions. So if you think again of a mechanical system, you need to specify the position, initial position, and initial velocity. Otherwise, you cannot predict the evolution of the system. Okay. Okay, so I will assume now that f, our function, is sufficiently regular to ensure that you have the existence and the uniqueness of the result of the problem. So the differential equation plus initial condition, which is called Koshi problem in the jargon. What does it mean sufficiently regular? Indeed, it's very low condition. It's enough if you know it that f is Lipschitz, locally Lipschitz. It means that more or less you have the derivative almost everywhere, or if you want, if you don't have the derivative, the ratio between f evaluating to close point divided by the difference of the point is bounded. So it's very low regularity condition. But this is enough to ensure existence, which is good, but also a uniqueness. And also uniqueness is important because if you have a system and you want to predict the future, you have to have the uniqueness of the solution, because otherwise you cannot know which is the good solution. And so I will denote here by the solution by phi depending of t, time, and depending also on the initial condition x at 0. You can also prove, this is a standard result that you can find in the book that I quoted before, that this function phi is admit the first derivative continuous with respect to time. So it's a function c1 in time, but also depend continuously on x at 0 if depends on condition on x0. You can improve the regularity adding other condition, but for the moment this will be enough. Then among all the class of all possible function f, you can do a first rough division, the linear one, which is in some sense the one where you have only monomial. So you only have variables xi that are present without any power or any function. And so in this case, indeed, you have your function f is a matrix times your vector x. In this case, you can find explicitly the solution, which is the exponential of the matrix times the vector. Of course, you have to define what is the exponential of a matrix. And if you didn't see this before, the exponential of a matrix, you can define it as using, if you want, the definition for the number. So it's the sum or all the integer n of the power of the matrix n divided to the n factorial. So if this series converges, then this is true if A is as a finite norm, then this function, this formula for phi define this exponential is the definition if you want. The other case is nonlinear one. It is all the other remaining cases. So where once you have the component to some power, the component with the logarithm, sinus, cosinus, and so on. Okay, and of course the more interesting case is the nonlinear case, because it's the one where you don't know exactly the solution, or you have to work a bit. Even if in the linear case, I will show you later on, you can still have some surprise. Then the last division is between autonomous versus non-autonomous case. What does it mean? So in the non-autonomous case, the function f doesn't depend on time. So if you think of forces, the forces are constant and only depend on, say, position and velocity, but they will not vary in time. Or you have the non-autonomous system where the function f also depend on the time. So even if you don't change position and velocity, because the time evolves, your force will also change in time. Okay. Of course, the non-autonomous case will be more difficult, while the autonomous is a bit simpler. So I will concentrate mainly on the autonomous one, but we will also see some result about the non-autonomous in the following. Okay. Alors, just one slide about the discrete time, because in many applications, of course, time is a continuous variable in the real life, but you can only have measurement, say, every day. If you study a population of animals, also human beings, you cannot think of studying with a continuous time. You have to do measurements that are done, say, every hour or every day. So in some cases, it's interesting to study dynamical system where the time is a discrete variable. So it's a mistake here. Of course, it's not R, but is N, the integers. And again, you have your X that define the phase state. You have still your function F, but now the evolution is just given by a map. So the new position, the new X at time, if you want a step N plus 1, is the application of F on the present time, so on the present step N. Okay, and again, you have to provide the initial condition. So this can be done, I say, it has been done. There are very interesting results, but because I have to make a choice, so it can be studied, but we will not do it because we don't have time. So I think it's interesting. I really think in many cases the only way to do, because the continuous time is not what you have. Also, if you think of data from COVID, which is a very large domain of research in these months, but you only have measurement every day. You cannot have the number of COVID patients or COVID death every second or every millisecond. And so you have to do a dynamical system study based on the fact that you have discrete time. You can try to interpolate, but the dynamics can be different. So it's interesting, but I don't have time to do this in this lecture. Okay. So, because now I'm interested in the case where f is a nonlinear function, in principle, it's very difficult to find the solution. So I'm not able to write x of t is equals some formula where you have the time evolution of x. And so the first thing that you can do is to find equilibrium point. So you have to find a point x star such that f is 0. This is important because if you remember that x dot is equal f of x, if you evaluate this on x equal x star, then this is 0. And so if you remember your lecture on calculus, if you have a function whose derivative is 0, a function whose derivative is 0, then this function is a constant, and this means that the x of t is a constant. So you have a constant solution. So if you find an equilibrium point, so a point x star, so you already find a very special class of solution, the one that are stationary, so the one that do not evolve in time. Okay. Alors, so then the next point is that once you have a stationary solution, you would like to know what happens if you start close by. So if I start close to my equilibrium x star, will I remain close forever, or at some point will I escape away? So this is the question about the stability of this equilibrium point. And there are few definitions. The first one is the one due to Lyapunov. It is called stability by Lyapunov. And the idea, I will do a drawing in the meantime that I will read it. So the idea is that you have your x star, which is my black dot. This means that whenever I fix an epsilon, so this is my epsilon, a small disk of radius epsilon, then there are a second disk, which is some radius, delta, maybe it's larger. And this implies that every time that I take a new solution starting from this larger set, then the orbit is confined in this smaller one for all the time. Okay, so this means actually that, okay, theoretically, you know that your system should be in x star in equilibrium, but once you do a measurement or once you put physically your system in some initial condition, it's impossible to fix exactly x star. But so if it's locally stable, actually it doesn't matter. If you do a small error, the system will remain closed forever to this x star. So you will not appreciate the fact that you are not actually on the equilibrium point. You can ask even a bit more, and you can ask that actually the system is asymptotically stable. That means that, okay, if you start close by, so if you start delta close to your initial point, then you can ensure that your system will converge to the equilibrium point. So you think of a small ball, and you put a small, I don't know, something that a balls that roll on these balls, but of course the stable solution is the one on the bottom. But even if you start close by, these balls will wrap around, and because of the friction, at some point we stop close to the equilibrium point. Okay. So now that you have this idea of stability, so remember the idea is for all epsilon there exists delta, or it exists delta depending x star. So every time that in mathematics you have there exists, is hard to do because you have to prove that this stuff really exists. So it is better to have some, say, practical condition that you can check directly on your system. This is what this can be done with the linear stability analysis. So again, you take your equilibrium point x star, which is so the zero of your function f, and then you compute the Jacobian matrix. The Jacobian matrix, so is defined here. So it's the matrix J I whose component, so Ij is the derivative of the component of the ith component of f with respect to jth component of the vector x. And so if you want, this is the generalization of the derivative. Once you have a higher dimensional vectors, a function of vectors, then the Jacobian is the good definition for the derivative. And once you have this Jacobian matrix, then you can compute the eigenvalues. So just remember a bit of algebra. You have to solve the equation determinant of J of x0 minus lambda times identity equal to 0. So this is So this is a polynomial equation of degree n in lambda. And so if you can find n different solution roots, so you have the n eigenvalues, it can be that some eigenvalues can be double because your eigen is a multiplicity larger than 1. So, but they're technical details, but they can be also handled in this case. And so once you have the eigenvalues, so the root of this equation, then it is to prove that if all the real part of these eigenvalues are, so have negative real part, then your equilibrium is asymptotically stable. So this is a really practical application because you found a point, which is the zero of some function. You compute several derivatives, so a matrix. You compute the root of this equation. They can be hard, they can be done numerically. In general, the roots are complex number, even if your matrix is real, because once you have a polynomial with real coefficient, you can have a complex root. But then if the real part of the roots are all strictly negative, then you have something which is stable. So it is very good, very simple to apply. So a small idea how this proof works. So let me do the proof in a one-dimensional case, just is easier to write it. So I have this is my equation, x dot is equal f of x. I remember that if f the x star is equal 0, so I define a function of u, which is x minus x star. So it's the distance with respect to the equilibrium. And then I would like to write my initial equation is one in the new variable u. So I just have to make the derivative of u, so which is u dot is equal to x dot minus x star dot. So let me write it. But x star is a number, so is a constant. So its derivative is 0. And so I have that the derivative of u is the derivative of x, which is 2f. Instead of writing of f of x, I will write as u plus x star. So x star plus u. Okay, up now is exact, is correct. And now I assume that u is small. So I assume that because I'm interested in the local stability, that I start close enough to my equilibrium point x star. And so if u is small, I can develop f in Taylor. So because I'm here only, I'm on one variable, I use a standard Taylor series. But if you have in higher dimension, you have to use the Jacobian, so the multivariate expansion. And so this gives me f of x star plus f prime evaluated in x star times u plus dot dot dot, which is say a square term in a u square. Okay, but if you remember that f of x star is 0, this tells you that u prime, so the displacement with respect to the equilibrium is equal to f prime of x star times u plus something is more. And so if, so let me write this just some constant times u square. So if now you assume that f prime of x star, so because the system is one-dimensional, x f prime is real. So I can say if this is small than 0, then you can take u sufficiently small such that, so let's say call smaller some delta, such that f prime of x star plus delta is also negative, plus delta plus c, sorry, is also negative. And this shows you that all this stuff here can be taken, say, let me call this is some, so this, sorry, so this is equal to some theta, which is smaller than 0. And so this means this is smaller some theta times u, because in some sense I said, okay, u square is small, so is I can write it like delta times u, and so delta is with c is put in theta, and so you have the equation u prime smaller or equal than theta u, and because theta is small, you know that the u is going to 0 exponentially, so this means the solution is u of t is exponential theta t times u of 0, and this goes to 0 as t goes to infinity. And so this shows you that if you take the only root, so the derivative negative, if you start close enough to the equilibrium, then you will reach asymptotically the equilibrium. A similar proof can be done in the general case where you have several dimensions. You just take norms and take the largest eigenvalues and so on, but the same proof can be done. So I will skip this part. So just now a small remark about a linear system, because I told you a linear system, it's very easy. Okay, it's not so true. So because there are some kind of matrices called non-normal matrices, which are defined by this equation. So a matrix is called non-normal if it doesn't commute with transpose. So if you take A times transpose A is different from A transpose times A. So this implies that this matrix cannot be diagonalized with an orthogonal vector. So you can diagonalize it, but the eigenvector will be not orthogonal. These are very interesting consequences on the dynamics. So here I'm studying a linear system, which is this one. So x dot is equal to A times x, and I study the two norms of the vector. So if you want the square of the mass or whatever is your vector, and I draw in the figure two cases. The matrix A1 is a diagonal matrix with eigenvalues -1 and -2. So because of the theorem that I just show you, you know that the equilibrium, this case is 0 because it's a linear system. So the equilibrium is asymptotically stable, and indeed you reach 0 by using the largest of the eigenvalues, -1. Indeed, here in this plot, in the inset, I show you the log of the norm, and you see that this line is a slope -1. This is the theorem that I just showed you. Let's now consider the matrix A2. The matrix A2 is not symmetric because you have one number 10 over here, but he has the same spectrum. The eigenvalues are again -1 and -2. And indeed, you expect that for T large, again, 0 is stable. And so you reach 0 with the slope given by -1. This is true. But if you look what happens at short time, you see this jump. So this means that if you are looking at your system, which is in this case linear, for short time, even if for a long time it will go to 0, for short time it will be away from 0. And so this is a problem, because if this time here is as the same size, almost the same size as the size of your system, the lifetime of your system, you know that in principle you will reach equilibrium, but in practice you never reach it. Moreover, what is important is that if this system in reality is a nonlinear system, and then you linearized, and you want to use the previous theorem that say, I compute the spectrum, if the spectrum is a real part negative, then I converge to the equilibrium. This is true, but this depends on how large you take the initial condition. Because if you take initial condition which is not so close to the origin, you will have this excursion, and then you lose this condition that was is here, that you have to start really close to initial condition. Okay, and so if you have no normal matrices, in some sense you can say, okay, the equilibrium remain stable, but the basin of attraction, so the set of points that will be attracted to this point, is very small. It shrinks almost to zero. But again, I remember, if you just compute the spectra of these two matrices, they have the same spectrum, -1 and -2. And so from a simple spectral analysis, we will not recognize anything different. It's only dynamics that will tell you the difference. And just to add some jargon, alpha or alpha is called spectral abscissa, and so it is the largest eigenvalues of the matrix A, while omega of alpha is called numerical abscissa, which is the spectrum of the Hermitian, so A plus A transpose, so the symmetrized version of your matrix A. And this is called reactivity. And what is interesting is that in biology, mainly in ecology, this idea of reactivity is known since a long time, since a really long time, because they were aware that in many applications in biology or in ecology, the matrix A is not symmetric, so they are dealing with non-normal matrices, and they observe this kind of jump away from the equilibrium before settle eventually on the equilibrium. So this is an important point, that even linear system can have something to tell you about the dynamics. Okay, so once you have the equilibrium, you can be sometimes can be happy to also have a solution. So you can find really a function psi that depends on time or also on x naught initial condition, which solves your equation. So once you are able to find this solution, then you can ask the same question: is my solution stable or not? And the answer is given by this result due to Poincaré, which is called orbitally stable or Poincaré stable. Again, I draw just a picture. The idea is that here is time. This is your function of psi over t. The idea is that whatever you fix a threshold epsilon, something like this, then you can find, I don't remember the code for that. So you can find a delta, so a tubular neighborhood of your solution, such that once you start inside this tubular net, so you start close delta, so it's close start, then you will eventually remain bounded close, say, to your solution, to your nominal solution at most epsilon. So if epsilon is small, even if you don't start exactly on your solution psi of t x0, indeed the solution that you get is really close, is epsilon close. Okay. A particular case of time-dependent solution which is interesting is the case of periodic solution, because there are many examples of solutions that are periodic in time because of cycles in the system. If you think of humans, we have the night and day cycles. It can be bacteria that also have cycles. So cycles are everywhere in our life, in the physics. And so it's interesting to study the periodic solution. So again, you should be happy or strong enough to prove that you have this solution psi, which is a solution which is t-periodic. So you have this capital T, which is the period, such that once you compute the solution at time t, small t, and you add the period, you again find the same function. In this case, what can be done? You can build what is called the Poincaré map. So you work in an n-dimensional system, which is your phase space, where you have this solution psi. Then you have to find a n-1 dimensional manifold, which is transverse to the flow. So if I try to do a picture, which is something like this, So assume that I in dimension 3. So here I draw a two-dimensional manifold, so a plane or something like a plane. So here is my solution that cross transversally. So this angle over here is positive. Okay, so this is the solution psi tx naught, and so this is my v. And so this n-1 dimensional manifold transverse to the flow. It means that you have this kind of plane of hyperplane of manifold that is crossed from one side to the other side by the solution. Okay, and again, so once you have this plane, you can, so because the orbit is indeed periodic, after some period the orbit go back. Sorry again. So it will cross again your plane or your hyperplane. So if you start from one point that I call x prime, then you end up after a period with a new point is called x second, and this is the Poincare map. So the Poincare map is the map that depends, of course, on the system, but also on the manifold V that you choose, that to each point x prime close enough to the x0, because this is only true locally. You cannot have, it's very difficult to have a global Poincare map. So given any point x prime close to x0, you will have a new point x second. Okay, so this is the Poincare map, and this is important because now you can prove the stability of your system by proving the stability of Poincare map. Indeed, you can prove that the map is stable if, again, for every epsilon, you can find a delta such that if you start close enough to your initial point x0, then once you iterate the map n times, then the iterate are close to the initial point. So you notice that because your map, your solution is periodic, you have that psi of t plus capital T is equal to 0. This means that once you apply the Poincare map on x naught, you get x naught, because by definition is a fixed point of the map. So this means that once you iterate n times a point which is close, x prime, then you remain close forever. You can also have this asymptotic stability, which state that, okay, you are close forever, but moreover, you converge to this point. Okay, and then indeed you can prove that this stability can be pushed back to the continuous flow. So all the flow will converge to the orbit, the reference orbit, the periodic orbit that you have. Okay, once you have a periodic solution, you can also use another theory, which is the theory done by Floquet. So let me explain the theory in the case of linear system, because it's a bit easier. In the nonlinear case, you have again to linearize, you can have some trouble, but there is a theorem by Antonov and Witt, also called Lyapunov-Antonov-Witt theorem, that tells you about the stability of a nonlinear system with a periodic solution. But I will present in the case of a linear system. So again, I have a linear system, so my function f is indeed just a matrix, but now depends on time, and this matrix A depends on time periodically. So it's a matrix that after capital T takes again the same value. Okay, the theorem by Floquet says that then once you have this system, you can find a matrix B and a matrix, so B is a constant, and you can find a matrix S which depends on time, so it's a function matrix, but which is periodic and invertible, such that the solution can be written as S times exponential BT times x0. So this is important because being S periodic, you can understand that everything is important is captured by B. Why this? Because if assume now that you are interested in studying T at x at T plus capital T, but this is equal by definition of S and T plus capital T time exponential of B. We already saw the exponential of a matrix times T plus capital T x naught. But then remember S is periodic, so this is equal to S of T. Here you have B T. I didn't prove it, but you can prove that for exponential of matrices, the same rule applied for exponential numbers. So the exponential of the sum is the product of the exponential, because in this case the matrix is the same matrix. So you have times exponential b t x naught, and then you recognize that this part here, sorry, this part here, I don't know why when I touch it disappear my right. So this part here is almost the x at time t, and so everything that really matters is how this exponential bt it behaves in times. Okay, so this can be made more rigorous. Okay, I can give a sketch of the proof why this is the case. I forgot. So, and moreover, you have this expression for s. So let me show you this, why this is true. So let me write again. You have this equation, and then you write x. You make a change of variable from x to new variable y using this matrix S, and I will show that this matrix S will satisfy this equation, and the new equation for y will be y dot is equal to b times y, where b is the matrix that I showed you in the slide before. Okay, so how to do this? But you take the new equation linking x and y, you differentiate, so you have x dot is equal s dot times y plus s times y dot, because I remember s is a function of time. Then instead of x dot, you write a times x. I just didn't write dependent of t each time, but of course s and I depend on time. And then you replace x by sy, so you have a sy. And then if I conclude the first line, you have s dot times y plus s. Instead of y dot, I put b y. And so if you put this for all y, because this is true for all x, you have a linear system, then you can recognize that s dot should solve as minus sb, which is the formula that I showed before. But now, because y dot is equal by, we already know, sorry, the solution is y of t is equal exponential bt phi times y0. And then if you insert this information in the link between x and y, this tells you that x of t is equal s of t times exponential bt y0, but in this case y0 you can write x0. So this proves in some sense the first part of the Floquet theorem. The important part is the next one, where you can prove the stability. Indeed, as I told you before, this matrix exponential bt, where t is the period, is the main part of the solution. It is called C, which is the monodromy matrix. So it's the matrix that you obtain once you evaluate the solution after one period. And then the eigenvalues that I call rho of this matrix C are called characteristic multipliers, and they are related to the eigenvalues of B, that I call mu, that I call characteristic exponent. And then you can prove this theorem due by Andronov and Witt, that tells you, which is very similar to the one that I showed before, that if all the real part of the characteristic exponent mu are negative, then the orbit is stable. So this is important because now again, if you are able to compute the matrix C or the matrix B, in principle it's quite hard, but you can have estimate and so on. Then if you have these matrices B and C, B or C, you can compute the spectrum, and so you can conclude about the stability of the periodic solution. And a similar theorem holds true for the nonlinear case. So the theorem by Andronov, Witt, and Lyapunov. Okay, just few notes, and then I think we are almost done. The first note is that you always have one eigenvalues, one characteristic exponent equal to 0, because this tells you that along the direction of the flow, you will not change anything because you are moving along the flow. So neither you expand nor you contract. So you know that you only have one eigenvalue equal to 0. Then there are some way to compute S or Y that I tell you. It depends case by case, problem by problem. But what is important is that you have this relation. So the product of the eigenvalues of C are the exponential of the integral of the trace of A. So maybe a complicated formula, but if you consider in the case n equal to 2, so only 2 dimension, because you know that the one eigenvalue is 0, so this means that the rho is equal to 1. By using this formula, you already have the second one. And so if you the trace of the matrix is simple, just compute the sum of the diagonal elements, you do an integral. And so if the result is smaller than 1, then you have stability. If it's larger, you have instability. So in some cases, I repeat, it can be quite easy to prove the stability or the instability or the solution. Okay, I don't know, Stefanella, how many minutes do you have?
Yes, you have, because we start late. No?
Okay. So I have still a few slides, but interrupt me when it's time to stop, and I will continue next time. So just a few remarks. Among the periodic solution, the limit cycle are the one that are more interesting one. So it's the same difference that if you have an harmonic oscillator, something that you may be very well known, there are a lot of periodic solutions. Indeed, all the solutions are periodic, so they are too much. And so in some sense, it's more interesting to have isolated periodic solution. So a periodic solution such that in a neighborhood, this is the only one. And so there are real application in physics, biology, and so on. However, find limit cycles is difficult. There is a still open problem written by Hilbert in the more than 1 century ago. Is the second part of the 16th Hilbert problem, which is determine an upper bound of the number limit cycle in a very simple case, polynomial differential equation in the 2-dimensional plane. So it's a really very simple framework. You have a plane, so you have 2 equations, x dot is equal something and y dot is equal something, and the function are polynomials. So almost the simple stuff that you can do. And so to know how many limit cycle do you have is still an open problem, and you would like to have this number or this bound in terms of the degree of the polynomial, of course, or the coefficient. The only thing that we know, which is already 30 years old, is that this number is finite. So it's due by Ilyashenko and Ekal, so in 91, 92. And so we know that this number is finite, but we don't know exactly how many limit cycle you can have. This theorem is a proof by existence, so I think the bound is exponential of n, so it's not a real bound. In some cases, we expect the bound to be linear in n, but we don't have proof. So the question or the issue of finding limit cycle is a really difficult task, of course. But of course, it's one really interesting one. So I think it's worth studying, worth putting energy to try to understand the limit cycle, how many they are, how do they behave, and so on. Okay, so we start with the simplest example, equilibria, so stable solutions that are just point. Then we pass to solutions that they vary in time initially in any way, but then we start to the periodic one, and now to limit cycle. And so, okay, sorry, I forgot this one. So what can be used to find limit cycle? So if you are in a plane, you can use the Poincaré-Bendixson theorem. I don't know if you are aware of this theorem. It's a very beautiful one, which in some sense say the following. So let me draw a plane. The theorem says if you are able to prove that the existence of a region, so this annular region, which looks like an annular one, where f, so the function of which is your x dot is equal f, is always different from 0, and such that the flow never escape from this region, then you can prove the existence of at least one limit cycle. So this is a result by Poincaré-Bendixson, which is in some sense the only one that you can use in the plane, but of course it's difficult to have a bound on, as I told you before. What let's say, so is really important is a 2-dimension and the plane. So the same result is not true, for instance, on the torus. So just to show, or if you take a 3-dimensional space, the important point is that in the plane, a closed curve divides the plane from an inner part and the outer part. And this is not true in the torus. So in the torus, you cannot use the Poincaré-Bendixson theorem. The other possibility in general, so in higher dimension, is to use the Brouwer fixed point theorem. What does it mean? It means that you suppose that you have again your T-periodic solution. And so this means that, so you have your initial space. I don't know, let me draw as a plane, but it can be in any dimension. And suppose that you can find a set such that after a period, so this is my set, is mapped into inside. Okay, so you have an application, which is the Poincare map, that put your initial set into a smaller one, which is contained in the previous one. Because this map is continuous, is even more continuous, but it's continuous by initial condition, then you can use the Brouwer fixed point theorem that tells you that you have a continuous map that maps a set into itself. So if you want a disk into a disk, then you have at least a fixed point. A fixed point of the Poincare map is a periodic orbit of the system. So this is the other possibility to prove the existence of a periodic solution or limit cycle using this Brouwer fixed point theorem. But again, you have to prove the existence of this set, which is mapped into itself after a period. So it's not so easy in general. Okay, so the last, okay, I think I will not finish today for the dynamical system. I put too many stuff. Okay, one interesting example of limit cycle is the one provided by the van der Pol oscillator. So I don't know if you are already aware of this. So you have the second order differential equation, and which now depends. So if you think this, it can be an oscillator, but where the friction term is not a constant, but depends on the position. So this is the velocity if you want. If you put these terms equal to 1, then you have a linear oscillator, something is damped or excited. But if this part depends on the state, you have a nonlinear damping. And let us study the case where mu, the parameter is small, because you can have the regime where mu is large. Okay, and then in this case, you can change coordinate. Here the coordinate are called Leonard coordinate by the work by Leonard. And the coordinate as following: you define x dot is equal to this function. What is this function? It's just the integral of 1 minus x squared. So here is x because the integral of 1 minus x cubed divided by 3 is the integral of minus squared. So you put here so if you think as a potential, here you put the derivative of the potential, and then you take off y. So this is my new equation for y, for x, sorry. And for y dot, I put y dot is equal to x, and if you do this, then you can prove the existence of a limit cycle. How you can do this? Okay, you can compute the zero isocline, which is the set of points for which this function f is so, which is, if I, okay, over here. So this is the set of points where this function vanishes, and so is where the x dot is equal to 0. So if you draw on this, this is my phase plane, is the point where so x at 0, so you only have the vertical component of your vector field. So along this curve, so I hope you can see it, the vector field points vertically, up and down, depends on the sign of x. So if x positive, because you have y dot positive, then it points upward. While if x is negative, because x dot is x, it points downward. And then if you look a bit how it works close to the origin, you can compute again 0, 0 is the only equilibrium, so my x star previous. You can compute the Jacobian, easy, just compute the derivative for x prime with respect to x and evaluate it in 0, then compute the derivative of x prime with respect to y, evaluate in 0, so it's -1, and so on. So you get this matrix. You can compute the eigenvalues that are given by this number. Then you can show that if you are close enough to the origin, and if mu is positive, then you are escaping from the origin in such kind of spirals. You can see this because if I remember the theorem that I showed before, the real part of lambda is mu over 2, And so if this part is positive, then the equilibrium is unstable. And so you are spiraling outward from the origin. While if the real part of lambda is negative, so mu is negative, then you are entering in the origin. So the origin is stable. Okay, so in this case, I have a stable focus, while if mu is positive, I have an unstable focus. And then if I did this plot using MATLAB, but you can do using whatever software you like it. And then you can see that from the inside, you are spiraling outward, but from the outside, you are spiraling inward. And so by Poincaré-Bennigsen theorem, you can prove the existence of a limit cycle that is the orbit that is more or less plotted here. Okay, so this is not a proof, it's just a picture, but you can prove that the Van der Pol oscillator has one and only one limit cycle, which is stable if mu is small enough, so smaller than 2 in absolute value. Okay, and so we can say that a limit cycle was born from a bifurcation, because if mu is negative, you have a stable point and you are attracted to the origin, while if mu is positive, you have the origin which is unstable, but the limit cycle was born. So now I was supposed to start to speak about bifurcation, but it's already 8:10. Maybe we can start there. I can have a question if you have question, remarks, discussion, whatever you want.
Thank you very much. Wow, it's challenging to present. I learned stuff. Very nice. Floquet theory in 10 minutes is challenge.
I hope it was clear enough.
Yes, yeah,
so,
very clear. And actually very good remark about non-normal metrics. Very useful in this moment of COVID things, SRI model. Very interesting. So the students, well, start thanking Timoteo first, not to forget to thank the speaker. Otherwise, I forgot. So let's thank the speaker. Open the microphone and let's thank the speaker, please.
Thank you for listening.
So, question, do not be shy. Oh, we are here to learn, so you can ask questions. Let's see if there is.
I will share my slides so I can send them by Stefano tomorrow or tonight.
Yeah.
And then I will add some references to book, the one that I will give you, some papers and so on if you're interested. But do not hesitate to ask me. You have my email. Okay, it's not in this. Okay, I know maybe you cannot see my. You can see my email here, so you can write me, and I can. You can have a chat. I can send you papers and so on. So, okay, do not hesitate.
Any question? They're shy. There's. Yeah. Pode perguntar.
Yeah, it can be in Spanish and Portuguese. I can try to understand, but I will answer in English.
Yes. Let's see. I try to see if there is a in the chat. I lost the chat on my screen, so I try to the YouTube. I lost YouTube on my screen, so no. They're very silent. Well, it's the first lecture. They have to break the ice. No, they have to break the ice. Every time the second lecture, they will be more talkative. They're a little bit shy. Victor's? No, any Victor speaking? Okay. But anyway, it was very clear. Thank you. It was fantastic.
Thank you. Thank you to you.
Yes. So
yeah, I mixed together stuff that normally, at least in Belgium, taught at the second year, but also stuff in the fourth year. So I went across a CV, a curriculum in mathematics for almost 2-3 years of study. So it can be that not everything is clear enough because I really span 2-3 years of research. So
no, it was very clear, at least for me. Okay, so we can. So if there are no questions, we let Timoteo to go for dinner. You know, imagine it's dinner time. Yes. So Igor, he's looking for the next. Thank you, Igor. So we resume next Thursday at the same time. So remember that the YouTube, I put YouTube just at 2 o'clock because I have to have the time to do this. And remember that you can ask questions. Here is an interactive classroom. So we are all here to learn. And so there is do not be afraid to ask questions. And Timoteo is a fantastic teacher. So I'm sure that he will be happy to have a question. Okay.
If you want next time, you can start with a 5-minute question about the lecture of today, because now maybe you are receiving too many information at time. So
yeah,
you can think of and Thursday ask some question.
Yeah, great. Okay, so we thank Timoteo, and actually I hope that in the future Glaston can give us a mini course on Poincare map, so to reinforce some of this what was spoken today. So see you all next Thursday. Thank you once more, Timoteo, for the wonderful lecture. So bye-bye.
Bye.
Bye-bye to everyone. Ciao.